Every material you've ever touched, from the silicon in your phone to the cotton in your shirt, was discovered largely by accident or painstakingly slow trial and error. Imagine a library containing a book for every possible combination of atoms. Almost every book in this library describes a material that has never existed. We have spent our entire history wandering this library, picking books off the shelf at random. Now we've built a librarian that can read the titles without opening the books. This librarian is a neural network, and its language is chemistry. Scientists feed it thousands of known materials, showing it an atomic structure and pairing it with its measured properties, like strength, conductivity, or melting point. The AI isn't memorizing facts. It's learning the underlying grammar of physics that connects atoms to behavior. It begins to see the invisible rules that dictate why glass is brittle but steel is strong, developing an intuition for the atomic world that surpasses human capability. Predicting a material's properties from its structure is one thing. The truly revolutionary step is asking the inverse question: what structure will give me the properties I want? This is called inverse design. You can ask the AI, design me a material that is as light as plastic but conducts electricity like copper and is transparent. The network then works backward, dreaming up novel atomic configurations that should, in theory, fulfill these exact criteria. It's no longer discovery, it's invention at the atomic scale. To navigate the near-infinite library of materials, the AI creates something called a latent space. Think of it as a map. On this map, every possible material is a single point of light. Materials with similar properties, like different types of steel, are clustered together in glowing nebula. Unexplored regions of the map represent completely new classes of materials. The AI can navigate this space, traveling from a known material toward a region with desirable but unknown properties. This isn't magic. It's built on a bedrock of computational chemistry. The AI's predictions are often verified using incredibly intensive simulations based on quantum mechanics, like density functional theory, or DFT. DFT essentially calculates how all the electrons in a proposed atomic structure will behave, which in turn determines every single one of its properties. For decades, these calculations were too slow to be practical for discovery. Now, the AI acts as a smart filter, proposing only the most promising candidates for these expensive computational checkups. The process doesn't stop with a simulation. The most promising AI-designed blueprints are sent to automated labs. Here, robotic arms mix chemicals, lasers synthesize tiny samples, and sensors measure the real-world properties of the brand-new material. This data, the ground truth of whether the AI's dream was accurate, is then fed back into the neural network. It's a closed loop of design, creation, and learning that accelerates the pace of discovery from decades to days. What does this actually create? Researchers have used these methods to design new solid-state electrolytes for safer, more powerful batteries. They've conceived of new catalysts that can capture carbon dioxide from the air with unprecedented efficiency, or new metal-organic frameworks that can store hydrogen fuel more densely than ever before. These aren't just incremental improvements. They are fundamentally new substances, imagined by an artificial mind to solve very human problems.
Monotony has grown fast. Nearly 2,700 people have watched in the last few weeks, yet less than 0.03% are subscribed. It would mean a lot if you joined by hitting subscribe. And again, thanks for watching.